Question 6. So we have here a bunch of information, and then we need to calculate the tensile force required to produce the pre-strain in the rail required by the engineer. So this is the pre-strain of the rail. First of all, we need to think, what's this question about? Well, it's a Young's modulus materials question. So what is the Young's modulus? Young's modulus is equal to stress divided by strain. We want to find what the force is. So to find that, we're going to first of all need the stress. So let's rearrange that to get stress. So stress is equal to Young's modulus times by the strain, which is equal to, the Young's modulus there is 2.0 times 10 to the 11 times by the strain there, 3.0 times 10 to the minus 4. Let's use calculator. 2.0 times 10 to the 11 times by 3.0 times 10 to the minus 4 gives us, use the ENG button, the engineering button, to change it into a nice standard form in powers of 3. So that's equal to 60 times 10 to the 6 Pascal. Then we need an equation which tells us what the force is. So we know what the stress is, we want the force, and we know what the area is. So we're going to use this one. Stress is equal to force divided by area. So stress is equal to force divided by area. So the force is equal to the stress times by the area, which is equal to the stress, which was the value we just calculated, 60 million, times by the area, which is up here. Just check its units. Yes, it's in base units. 7.5 times 10 to the minus 3. Which is 450 kilonewtons. So 450,000. So that's 4.5 times 10 to the 5 newtons, and that's to two significant figures as well. Calculate the elastic strain energy stored in a rail of unstressed length 45 meters when it's pre-strained, as in this part here. Right, we need the energy stored. So this is the energy stored in a stretched material. So let's write that down to start with. Energy stored is equal to a half times by the force times by the change in length. Okay, so we need to find out what the change in length was, because we don't know that yet. We know the force of the extension, that's that value, and then we can work out the energy. So the strain is equal to, this is tensile strain, delta L, the change in length, divided by L, the original length. So delta L divided by L. We want the change in length, so delta L is equal to strain times by the original length L. The strain was back up here, 3.0 times 10 to the minus 4 times by the original length, which is there, 45 meters. So let's put that in our calculator. 3.0 times 10 to the minus 4 times by 45 gives us 0.0135 meters. So that's the change in length. That's how much the piece of rail is stretched by. So now we need to go back to the energy stored. So let's just cordon that off there. So the energy stored is equal to a half times by the force, 4.5 times 10 to the 5, times by the change in length, which is 0.0135. So we need that value times by a half times by the force, 450,000, and that gives us 3,037 joules, which is 3,000 joules to two significant figures. Calculate the temperature at which the steel rail becomes unstressed. Okay, so this isn't directly on the specification, this is an applications question which you need to read and understand what's going on in this question. So as the rail heats up, it expands, and when it reaches its original length, which was 45 meters, then it will no longer be either in tension or compression, so it won't be stressed at all. So what we need to work out is, this is the amount of strain for each degree Kelvin, which is the same as a degree centigrade. So it's 2.5 times 10 to the minus 5, and that's for each degree Kelvin. And this is the amount of stress that it gets at 8 degrees. Sorry, the amount of strain that it gets at 8 degrees. So we need to take this value here and divide by this value here to find out how many degrees it will need to move in order for the strain to be reduced to 0. So we want to do 3.0 times 10 to the minus 4, and we divide that by 2.5 times 10 to the minus 5, and that gives you 12. Just to double check, 3.0 minus 4 divided by 2.5 minus 5 is 12. So the temperature change will need to be 12 degrees. It starts at 8 degrees, add an extra 12, gives you 20 degrees Celsius. Okay. Question 6.4. Explain why the engineer does not use the highest observed temperature at the location on the railway track to determine the amount of pre-strain to use. Well, they don't want to use either the highest or the lowest, because in that case the rail, when it's under normal conditions, will always be under stress, which is what you want to try and avoid. So the actual value to use would kind of be the average or the most common temperature at that area, because that will give you the least stress for the most amount of time. So the engineers should use the average or most common temperature to reduce the maximum and minimum strain the rail is put under. So you don't want to use anything at either extreme, you want to use something in the middle so that it can move backwards and forwards between those two extremes. So you've got the minimum there, the maximum there. You don't want to use either of these, because if it's over here then you've got that much stress. You want to use something in the middle to minimise these two values, so as the temperature moves backwards and forwards you are somewhere in the middle. Right, so the maximum minimum strain of the rail is put under, therefore the rail will spend least time under stress. Okay, and under less stress as well. Right, well that is the first paper. Thank you for viewing this video. I'm going to be doing a lot more of these videos, so please keep your eye on my channel. If you found this at all useful, I would really appreciate it if you could share it with your friends in your school and in other schools. And if you have any requests of exam papers that you want me to try and go over, or questions that you want me to try and do, then send me information about those in the comments section. And good luck in your exams. Thank you.